So now we're going to start our discussion of higher order linear differential equations. First, let's talk about what they are. Here is an nth order linear differential equation. It's a very specific form. So you notice, among other things, all the y's are on the left. There's a function of x on the right. And the left side takes this specific form. So specifically, there's a function of x times the nth derivative of y, and a function of x times the n minus 1th derivative, etc., all the way down to a function of x times the 0th derivative. So in other words, just y itself. Okay, so it's a very specific form. And it turns out that the nature of this form allows for a particular kind of analysis. So the first observation I want to make is that this left side of the equation can be thought of as an operator acting on y. So in other words, you can think of this as something where you put a function in, you put y in to this construction on the left side, and then something comes out. So you can view the differential equation as that we're looking for something that we can put in to this operator that we're calling L. L for the left side, let's say. And that then what will come out is this, you might say, target function called g of x. Okay. All right, so what can we say about the terminology here? We call this an nth order differential equation. That makes reference to an easily observed detail about this differential equation, and that is that the highest derivative is the nth derivative. So order just means what's the highest derivative in the equation. No big deal. Okay, linear. This is a more interesting thing to talk about. What do we mean by saying that this is a linear differential equation? Very importantly, we do not mean that some specific functions of x in this equation have to be linear. Absolutely not. We're not saying that that's a linear function. We're not saying that y is a linear function. We're not saying that these coefficients are linear functions. Nothing of this sort. What we're saying is that this operator is a linear operator. So the L, maybe it doesn't stand for the left side of the equation. Maybe it stands for linear. This is a linear operator on y. So what do we mean by saying that this is a linear operator? And keep in mind what this operator does is it takes a function as its input, and then it gives another function as its output. And we've talked about linearity before, specifically when we were talking about determinants. It was part of what we used to define the more sophisticated idea of multilinearity as applies to determinants. So in this case, linearity means the analogous thing. It's linear. This operator, representing the left-hand side of the equation, is linear in the sense that if you put a linear combination of inputs into it, then you get that same linear combination of the individual outputs. Okay, so linear combination in, linear combination out. Okay. Okay, so now let's confirm that this form here actually does have this property. It's not immediately obvious. I mean, you see all sorts of other things around. I mean, that function, that might make a difference if this function is trigonometric or something. How do we know that this form here actually has this property that we're asserting of linearity? And this is just a matter of direct checking. And here we go. We're going to compute the left-hand side of the expression that we're interested in. So notice that in order to do so, I have to take this linear combination of functions and I have to plug that in to my linear operator. So I've got to take this, plug it in there, which then gives us this, something along those lines as its output, namely that. So notice all I'm doing is taking this function, taking various derivatives from the nth derivative all the way down to no derivatives, and then multiplying by some coefficient functions, exactly such as is described by that form. Okay. Okay, so what does that give us? And what can I do with this expression? Well, conveniently, we know that derivatives have certain nice properties. I know that the derivative of a linear combination of functions is a linear combination of those individual derivatives. And that's true of the nth derivative, true of the n-1th derivative, true of the blah, 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 continuing more and more derivatives, and of course, it's true when you aren't taking any derivatives. Well, nothing happened there. Okay. Now, notice that I can take all of the y1 terms, the nth derivative of y1, there's an n-1th derivative of y1, etc. I can pull all of those terms over to there. Notice that there is a common factor of c1 in all of these terms. That comes right out. And what we're left with is coefficient times derivative, coefficient times derivative, coefficient times, well, the 0th derivative, so likewise there. So all I did there is collect terms, and then analogously, the y2 terms all collect like so. So all I did is move terms around there, and then I make the realization that, well, in fact, then this is exactly L of y1, and this is exactly L of y2. And these are exactly this form up here applied to the functions y1 and y2. And so as required, we have showed that that is equal to that, and therefore this operator is linear. Confirmed. Okay. Moving along. A little bit of terminology. If the right-hand side function is equal to 0, keep in mind that this function g of x is the right-hand side of the differential equation. There it is. If that right-hand side is equal to 0, we say that it's homogeneous. This is a borrowed bit of terminology. Recall in Chapter 1 we talked about matrix equations, and if the right-hand side of a matrix equation or a system of equations was equal to 0, we used the term homogeneous. So this is the same motivation here. Okay. Then there's this idea of an initial value problem and initial conditions. This is another borrowed concept. You'll recall that previously, when we were talking about first-order differential equations, we talked about initial condition on a differential equation, and the combination of the differential equation and the initial condition was an initial value problem. We do a very similar thing here. An initial value problem is the pair of a differential equation and prescribed values. We'll talk in a moment about why it is that we have to prescribe more than just the value of the function y. We have to prescribe values of y and y prime and all the way up to the n-1 derivative. Okay. All right. So there's a big theorem we're going to make a lot of use of in this class. I like to call this the existence and uniqueness theorem for nth order linear differential equations. I'll talk about why we call it that in just a moment. Here's what the theorem says in the broad strokes. We'll get to the details in a moment. If certain conditions are met, talk about those in a moment, under certain conditions, what this theorem says is that this initial value problem has exactly one solution. Notice that this is an initial value problem. There's a differential equation here. That's an initial condition per our definition up here. Prescribed values of various derivatives all the way up through the n-1 derivative. So this is exactly our definition of an initial value problem. And what the theorem says is that this has exactly one solution. Okay, so you can see now why we call this the existence and uniqueness theorem. This says that the solution exists. The solution that we're looking for to this initial value problem. That solution exists. But it also says that there's only one solution to this initial value problem, thus uniqueness. So it's a very natural name. We put the terminology, I think, to call this the existence and uniqueness theorem. And of course, this is an existence and this is an existence and uniqueness theorem for initial value problems involving nth order linear differential equations. Okay. All right. Now there are some conditions we do have to talk about. This is not true for all initial value problems. Here are the requirements. These coefficient functions have to be continuous. That's a requirement. If these functions are not continuous, then the theorem does not apply. And we would have to worry about the possibility that there might not be any solutions or there might be multiple solutions. This right-hand side has to be continuous. Again, that's part of the deal. That's part of the condition of the theorem. And lastly, this lead coefficient function can't be 0. If it's 0, then the theorem simply doesn't work, and we'll see why soon. That again, it's just one of the conditions, and if that condition is not met, then you cannot invoke this theorem. Okay, so those are the 3 conditions. Now make sure to check those conditions when you apply this theorem. And with those conditions satisfied, you get the desired result. Okay. By the way, we're not going to prove this theorem. So the proof is beyond the scope of this course. Okay, so very quickly now I want to go back and finish a thought. We were talking about this terminology, initial value problems, and in particular we were talking about these numbers being initial conditions. And the question comes up, well, why do we have to prescribe values for not just y? Why do we have to prescribe values for y and y prime and all these other things? And the short and sweet answer to that question, in my opinion, is because this is the information that, when included with a differential equation, gives you this theorem, namely that there is, in fact, exactly one solution. And if you prescribe less information, if you prescribe this and maybe a few of the derivatives, but you don't give that information, you won't have this feature of having exactly one solution. In fact, you'll have many different solutions. In fact, you can see that you'll get many different solutions without too much trouble, because you could just make up a number to be this unprescribed value. This theorem says you'd get a solution. But you could also make up a different number to be that unprescribed value. This theorem says you'd get a solution for that as well. And so you can just construct, using this theorem as it is, multiple solutions if you incorrectly define what an initial value problem is. In other words, if you incorrectly define what an initial condition is. So we make this choice, in short, we make this choice for what an initial condition is because that's what makes this theorem work. That's what makes this initial value problem have exactly one solution. We use it because it works.